Okay, so let's get started. Okay, so yesterday I did a review session for the midterm. Yeah, you guys here can hear me? Okay, so yesterday I did a review session for the midterm. Please, okay, are we gonna? Okay, so I mean, there's an emphasis on cyclic groups and on Lagrange's theorem. I think I emphasized this many times. Okay, so please study that. And a tip is that don't go exhaust yourself on the stuff from the beginning. Don't go study the stuff and don't go exhaust yourself on the stuff from the beginning. Just study the stuff from groups and onward. Okay, this is the most important things. Okay, don't go exhaust yourself on like bijections and inductions and things like that. Okay, yeah, are we good? Just study a lot of groups, cyclic groups. Make sure you know them. And Lagrange's theorem, Fermat's theorem, all the exercises that I suggested and I said left as an exercise, do them. Okay? Yeah. What
the whole way? Did you need to like have any study them?
What do you mean cycles? Oh, symmetric groups, you mean? Yeah. Yeah.
Yeah, we need to study.
Everything I said you need to study, you need to study. Okay. Please, okay, so again, it's not okay, let's get back to where we were. Yeah.
The following.
I mean, are you guys comfortable with the symmetric group or not?
That's kind of hard.
It's kind of hard. Okay, so let's not worry about it then. Okay. Okay, so symmetric group, you won't have any question on the symmetric group on the midterm. Okay, great.
That's a lot of information.
Yeah, exactly. I mean, it's a lot of information. So I did my part. Now you guys have to do your part, right? You guys have to do your okay.
Study everything in.
Okay. So I gave a lot of info. I think what's missing is that I give you the midterm like 2 days before you complete it, and then you come and write it. That's what's missing. But okay. So please study hard. Cyclic group, Lagrange's theorem, and you should be fine. Okay. Know everything, and don't go exhaust yourself on bijections and like induction, things like that. Okay. So study more on the groups part, cyclic groups, things like that. Okay. Big groups. We call that an homomorphism. Well, it's a function. Guys, if the function phi from g to h such that
All the operations are coordinated.
phi of xy is phi of x times phi of y, where the operation is happening in g on this side here, and this operation is happening in x. Okay, I will drop the dots, I will drop everything else. Okay. Now we have to look. Yeah, we will define. We can give one more homomorphism first. Let you be a group. And N a normal subgroup of G. Okay, then G mod N is a group. The map. I'll call it phi sub N from G to G mod N. That sends the element G to the coset Gn is a group. Okay. Let's prove that. I mean, that should be fairly straightforward, I guess. Okay. Can you guys hear me who are attending? Virtually? Okay, great. Now let's prove that. Pi n of G1, G2. What is that equal to? This is just G1, G2n. Now, what do I know about G1, G2n? I know that the law of G mod n, this is just G1n times G2n. So just pi n of G1, pi n. Okay, so you can, if you have any normal subgroup of a group G, then you can find the homomorphism from G to G mod n. Okay? This is called the projection. Basically, you're just projecting everything. Okay, pi is for projection. The index n is just for the normal subgroup. Okay, now let's do a nice example. Now, take n is equal to E, the identity. The identity is a normal subgroup of G. Now, what can you say about G modulo n? G modulo n is just the set of cosets isn't that the sets of cosets of this subgroup? Really, what is that? This is just agree? If you multiply G by identity, you get just the set G. Now, how many cosets does the identity have? It just has many elements as G, right? The identity has as many elements of G cosets. So really, G modulo the identity, it's just isomorphic to G. Right? You see that?
Isn't it also equal to G?
It's not technically, yeah, okay. So when you say equal, this is a set, right? This is an element. Okay, G is an element. This one is a set. So they're not equal, but the homomorphism is very nice, right? You just send you just send a map from E to G modulo G. You just say to the coset, right? This is a coset, right? If the identity, if the subgroup is the identity, then this is a coset. This is just G. Okay. So this homomorphism here is an isomorphism. It's clear it's injective, and it's clear it's bijection. It's surjective. Okay. Great. I mean, to convince her, I mean, you know, it's something, well, it's not very, I guess it's not very convincing, but if G is finite, what is the order? Say G has 10 elements. G modulo E, how many elements does it have? 10, right? It's 10 divided by 1. Okay? Okay, so I mean, this is not the very convincing argument, but G modulo the identity, you just get back G. Okay? Just the natural isomorphism here. Just G to the coset G. Okay. Now, if you have G mod G, G modulo G, what is that isomorphic to? How many cosets does G have in G? 1. Exactly. So this is just the group, the identity group, right? The group 1. Right? So you send G. Well, the G mod well. To I mean, G mod G. How many cosets does G have? 1 coset, right? What is this coset? What is this coset? It's G, right? This is just EG. G. So really, you find a homomorphism that sends G to the coset GG is just EG. Okay. So G mod G, Again, look at the order of that. If G has 10 elements, G modulo G, how many elements does it have? 10 divided by 10, which is 1. Okay, is it clear here? Yeah, okay. Now let's define the kernel of a homomorphism. The kernel of a homomorphism, let phi of H be the kernel of a homomorphism. Phi is defined to be the set of G and G that gets mapped to the identity in H. Okay? So it's all the elements that gets mapped to the identity in H. All the elements that get mapped to the identity. So let's give an example. Consider the homomorphism, the determinant homomorphism from GLN R to R star, which is the non-zero real number under multiplication. What is the kernel of the determinant homomorphism? It's just all the invertible matrices that gets mapped to the identity in R minus 0 under multiplication. What is the identity here? Under multiplication? 1. Example. So the kernel of this homomorphism is all the matrices of determinant 1. Okay? All the invertible matrices with determinant 1. Well, that's the only one that is invertible. Yeah. But all the matrices with determinant. Okay? This is just a kernel. I mean, you can do one more example, which I've seen. Sn, the sign homomorphism from Sn to plus or minus 1. What's the kernel of the sign homomorphism? It's just the sigma and Fn such that the sign of sigma is equal. What's the identity in this group? What is the kernel of this homomorphism? What do I call the set of permutation that have sign 1? What do I call this group? So if the even permutations, what is the name of this group? The alternating group, right? Okay. Are we good here? It's clear, right? Just like finding all the elements that get mapped to the identity in the other one. Okay, now what are the properties of the kernel? Or let's do one more. Let's do one more. Consider phi n from G to G mod n. N here is a normal subgroup of G that sends G to the coset Gn. What is the kernel of phi n? Just the set G and G. What is the identity element of G modulo n? What coset is it? It is n, right? Now, what is the set of G such that Gn is equal to n? This is just n. Okay? Is that clear? Is that clear, everyone? Great. Now, what are the properties of the kernel? A group. And that G be a group homomorphism proposition. Let phi from G to H be a group homomorphism. And the kernel of phi is a normal subgroup of G. Okay, so if you have the kernel of a homomorphism, it should be a normal subgroup of G. Let's prove that. First, we prove it's a subgroup, and then we prove it's not. Okay, so proof. That the kernel is a subgroup of G. First, we show that EG belongs to curve I. Recall that the kernel is the set of element of G that gets mapped to the identity in H. Now, we have seen before that phi of G is equal to EH. Okay? Let x1 belong to kernel of G. Kernel of phi, sorry. And phi of x is equal to the identity in H. And phi of y is also equal to the identity in H. Hence, is what phi of xy, which is equal to phi of x y, it's EH times EH, which is EH. Yes. XY belongs to the kernel. Now, 3, we need to show that x belongs to kernel of phi. I need to get to the conclusion that x inverse belongs to the kernel of phi. Right? This is what shows that kernel of phi is a subgroup. The phi of x inverse, what does that equal? By the properties we proved last time, it's the phi of x inverse, and t of h inverse is t of h. So x inverse also phi. Okay? Just checking the properties of the group homomorphism. Of the subgroup, sorry. And then that's what you get. Okay? Any question? Yes. Yeah, this is left. Okay. So x inverse belongs to curve phi. Okay, now conclude that phi is a normal subgroup. That curve phi is normal in G. I know you have to, so let G be G. And x in curve phi. I need to show that Gx G inverse belongs to curve phi, right? This is what I need to show. If curve phi is normal, I need to show that for every G in G and every x in the kernel of phi, Gx G inverse belongs to the kernel of phi. In other words, I need to compute phi of Gx G inverse and show that this is the identity in H. Right? This is what I need to show. So what is that? This is a phi of G, phi of x, phi of G inverse. Well, x belongs to the kernel of phi. So phi of x, what is it equal to? It's equal to the identity in H, right? What do I get here? I get here phi G inverse. Okay, well, this is just phi G, the inverse, just phi of the identity in G is the identity in H. Hence, hence what? Hence, G. therefore is a normal subgroup. Okay. Is it clear? Very good. Any questions? Okay, I mean, I'm just checking the axioms, not the definition of a subgroup. Okay, so yes. Where? Here?
Yeah.
So what's anything times the identity? X, y times the identity is what? Right? You can cancel it. No, but those are elements in each. Okay? Is that good? Yes. Yes, you can also bring the inverse outside. That's very good. Yes. Okay? Great. Okay, so the kernel is a normal subgroup of G. So basically, if I give you a subgroup that is not normal, could it be the kernel of a homomorphism? No. If I give you a subgroup of a group G that is not normal, can this subgroup be a kernel of a homomorphism? No. Now let's give a small application on that. Or I think we'll just maybe let's wait and do one more theorem and then we can give an example. Another proposition. Now, if phi from G to H is a group homomorphism, then phi is injective only if the kernel of phi is the identity in G. So basically, a homomorphism is injective. You know, as a function, it's injective if and only if the identity in G is the only element that gets mapped to the identity in H. This is a bit something counterintuitive, right? Not counterintuitive, but I mean, if phi is injective, then it's clear that the identity in G is the only element that gets mapped to the identity in H.
It's a bit like with the matrices.
Oh, what do you mean?
I mean, if you have a matrix that
I see. So you okay? Yeah. Very good. Very good. You mean AX equal to 0?
Yeah.
Yes. It follows from that. Exactly. It follows from that. Why is that? Because matrix multiplication is a group homomorphism. You can figure a matrix A on Rn. Okay. Now, what is A x plus y? It's just AX plus AY. Right? So a matrix is also a group homomorphism. Forget the scalar multiplication in Rn. Just consider the addition. This linear transformation is a group homomorphism if you just consider the addition and you don't worry about the scalar multiplication, right? So that's true. Yeah. And then you know that an n by n matrix is invertible if and only if AX equals 0 is equivalent to X equal to 0 vector, right? If you have seen that. Yes. In H, exactly. It's the set of all elements that's ended in H. I mean, you can write it this way if you want. It's the kernel of phi. It's the inverse image of the identity in H. Okay. Okay, great. Now let's prove this. Phi is injective. Well, first assume phi is injective. Let's assume phi is injective. Assume phi is injective. Kernel of phi. And it's the identity in G. Now it's clear that the identity in G belongs to the kernel of phi. Thanks. phi of EG. Now what you have to show is the reverse, that if x belongs to the kernel of phi, then I must show that x is the identity. Now what does it mean that x belongs to the kernel of phi? From your like analysis course or from any other math course. If x belongs to the phi inverse of the identity, then phi of x belongs to this set. Or by definition of kernel, then phi of x h, right? If x belongs to the kernel, then phi of x is equal to EH. Right? It's the definition of the kernel. It's the set of all elements that get mapped to the identity in H. Well, what is EH? This is just phi of EG. So I have phi of x is equal to phi of EG. Now, if phi is injective, what can I say about x and EG?
They're the same.
They're the same. Very good. Since phi is injective, x is equal to EG. Hence, kernel of phi is equal to EG. Okay, this is the first step. This is this way. And it's more the obvious way, right? We haven't really used that the kernel is a group homomorphism. Well, we did use this as a group homomorphism by saying that phi of EG is AH, but I did not use the multiplication. Now let's prove the reverse, the converse. Suppose curve phi is injective. Suppose curve phi is 1, is EG. We need to show that phi is injective. Is injective. How do we show something is injective? How do we show a function here? Exactly. So let xy be in G be such that phi of x is I need to get the last line. What should it be? It should be that x is equal to y. Okay. Now phi of x is equal to phi of y. How can I deal with this? Can I do operations on this?
Yes.
Can I bring all the elements on one side? Let's say I multiply everything by phi y inverse. I can bring everything on one side, right?
Yes.
Multiply everything by phi y inverse on the right. You get phi of x, phi y inverse is equal to the identity in H. Right? So far so good? Yeah? Everyone?
Yeah.
Okay. Now, what do I know about phi y inverse? How can I deal with this curve? This is just
Phi 1.
this thing. Right? What else I know about phi? It's a group homomorphism, so what can I do here?
We can bring the x and the y together.
I can bring the x and the y inverse together. Far so good. So far so good. Everything clear until here? Good. Okay. Now what does it say about xy inverse? If xy inverse is equal to, if phi of xy inverse belongs to the identity, where does xy inverse lie?
In the sum.
Right? It means that xy inverse lies in the kernel. This means that xy inverse belongs to the kernel of phi. What is the kernel of phi by assumption?
just EG.
It's just EG. So xy inverse is equal to EG. So x is equal to and y is injective.
Because inverse is unique.
Why? If you want, you can say that, or you can multiply by y on both sides. Right? Okay, is it clear? Any questions on that? Any questions? It's tough. It's not obvious.
It's quite a lot of stuff.
Things. But these are the most important lectures in group theory. Like this week and the week after are the most important lectures in group theory. Okay? Then we'll finish with group theory and start with rings. But these are the most important lecture in group theory. Okay?
Yeah.
Pardon me?
Rings.
Yeah. Okay, so please try to know these proofs and then practice them. Okay. Now let's prove the first isomorphism. What does it say? A G be a group. The G be the G arrangement groups and phi from G to H a group of what? Or more. It's not the full statement, but this is one part of the statement. You just focus on this one part. Then G modulo curve phi, right? Curve phi the normal subgroup. So I can talk about G modulo curve phi, right? So it's a group. It's isomorphic to phi, which is a very cool. What the hell? Very cool, homomorphism. It's a very cool statement. But I mean, the work here has been done already. We have done the work previously. Okay? Great. Let's prove this theorem. It's a bit tough. I don't disagree, but practice it, okay? Let's look at this. Prove. Now, this is a space of cosets. I will just define a homomorphism. And check it's an isomorphism. Define, I'll call this map phi bar from G modulo curve phi of G. Right? This is the image of phi, basically, the image of G under phi. That sends a coset G modulo G curve phi to phi G. I need to show first, whenever I have a function is defined on a coset space, I need to show that this function is well defined. Let's prove that. I bar is well defined. So suppose G1 kernel of phi is equal to kernel of phi. I need to show that phi of G1 is equal to phi of G2. That's the conclusion I need to arrive at. Okay. Now G1 curve phi is equal to G2 curve phi. It means that G2 inverse, it implies that G2 inverse G1 belongs to the kernel of phi. This implies that phi of G2 inverse G1 is equal to the identity in H. Or in other words, phi of G2 inverse phi of G1, because phi is a group homomorphism, is equal to the identity in H. Can I write here? Is here okay? Now this implies that phi of G2 inverse phi of G1 is equal to the identity in H, which implies then phi of G1 is equal to phi of G2. So phi is equal to phi bar is equal to sorry, yeah, phi, so phi bar phi bar is equal to yes. Yeah, you can do that. So you say phi of the subgroup is the identity. Yeah, that's good. Yeah, you say that let's apply phi from here, right? Yeah. Okay. Yeah. I mean, really, okay. Yeah, you can say that. But here you get the set as an image, right? You get a set as an image, but that's perfectly valid. Right. Very good. Yeah, very good. Okay. Yes. This equality here, right? These are cosets of a group. G1H is equal to G2H implies that G2 inverse G1 belongs to H. Okay? Great. Now I need to show that phi is injective. Well, let's show first that phi is a homomorphism. Let's show phi bar is a homomorphism. So what's phi bar? G1 per phi times G2 per phi. This is just phi bar of G1, G2 kernel of phi, which is just phi of G1, G2. So just phi of G1, phi of G2, just phi bar of G1 kernel of phi, F bar G2 kernel. So this is indeed a group homomorphism. Now I need to show it's an injective group homomorphism. Let's do that. I will do something you might not really like, but let's do it here. Phi bar is injective. Now, what does injectivity mean? It means that if phi bar of G1 per phi is equal to phi bar of G2 per phi, I need to show that G1 per phi is equal to G2 per phi. Really, what you have to do here is just reverse the arrows. If you reverse the arrows from here, you go up, you get that. Okay, so suppose that phi of G1 is equal to phi of G2. Then phi of G2 inverse phi of G1 is equal to EH. Right? Is that clear? Everybody? Everybody, are we good? Not really, but yeah, it happens. I mean, when I first saw this theorem, I was like, what? So, okay, but this is the most important theorem. Is this me? Yeah, but we're gonna go faster. Okay, so this is the speed you should expect the lectures to be at. Okay, yeah. Yes. Where? Here? Oh, no, what is phi bar of a coset? Phi bar of a coset is just the phi of the representative. Okay? You have to show it's well defined, that it doesn't depend on representative. Okay. I mean, you know, when I was in Algebra 1, we did the 3 isomorphism theorems in one lecture. Okay, so. Okay, now phi is injective. I mean, let me write this down. phi bar. Or you know what? Let's do it the other way. Let's prove that the kernel of phi bar is just the identity in H. Let's show that the kernel of phi bar is just a trivial cosine. So if phi bar G1, if phi bar G curve phi is equal to the identity in H, what does that mean? This means that phi of G is the identity in H, right? Because phi of G curve phi bar of G curve phi is phi of G. Well, what does this mean? This implies that G belongs to kernel of phi. Which implies that G curve phi is the kernel of phi. So really the kernel of phi bar is just the coset curve phi. Now the coset curve phi is just the identity in G mod curve phi. Okay, that's one way to do that. So phi bar is injective. Okay, or you can do it the way we did it before and reverse the arrows out. Yes.
I just don't understand. G is in.
If G is in H, H is subgroup, then GH is equal to big H, right? So take a subgroup H and multiply it by little h in H. You get it, right? The two sets, right? Okay. So phi bar is injective. Now it's clear that phi bar is projective. Phi bar is surjective. Phi bar is surjective. Let y be IG. Then y is equal to phi of x for some x in G. X. Phi bar of x, the kernel of phi. Okay, that's the proof of the first isomorphism theorem. It's very important. Okay. Maybe, I mean, I'll wait. Well, let's talk more about the midterm. Okay, so this is tough stuff. Okay, this is tough stuff. It's not easy, but please be sure to practice it very well. Okay. Yes. You have to prove that the kernel of phi bar is the identity element of G mod curve phi. What's the identity element of G mod curve phi? It's the coset curve phi. Okay. Okay, so about the midterm. I said there are going to be 4 questions. Okay, so the first question is Euclidean algorithm. The second question is on cyclic groups. Third and fourth questions. Third question involves Lagrange's theorem. Okay. I mean, yeah. Fourth question. I mean, if I say this, it's going to be clear what's going to be.
It's going to be a mystery question.
So I mean, it's going to involve Euler's and Fermat's theorem. Okay. Write this down. Don't look at me. Okay, like write this down. It's important that you do that. Okay, so the first question is the Euclidean algorithm. The second question is a question on cyclic groups. The third question is on Lagrange's theorem and possible applications. And the fourth question is on Fermat's and Euler's theorem. Okay, I don't know what more I can. I have to give you the questions. This is the next step. Okay.
Why are you being so kind to us?
I just want you guys to do well. Okay, that's what I want. And again, I know it's a bit challenging. Now I've heard anyways, it's a bit challenging. You guys are working hard. So again, there's still a lot of questions that I can give you. If I tell you the questions on cyclic groups, you don't know what I can give. Okay, and there is one common question that is very important. I think it's better if I solve it because I've been asked about it like 15 times so far. So it's better if we solve it. I mean, if you can wait, and it's important for the measure. So it's enough. The question is, if P is a prime and P congruent with 3 mod 4, show that x squared is congruent to -1 mod P has no solution. Okay, I love this as an exercise, and many of you, like 10, maybe 15, I can't remember. I couldn't keep track. After like 10 students asked me the question, I didn't keep track of how many students asked me that question. Okay, so I will do this exercise. It's a good exercise. I mean, I suggested it in class and didn't do it. And I strongly urge you to do it. Now the thing is, there are many ways of proving that, and many of you have come up with nice solutions. Now the thing I had in mind is to use Fermat's theorem. Okay, so here, what is? I mean, you can do it with Lagrange. Okay, so you can do it with Lagrange's theorem. So first I can write P is equal to 3 plus 4k for some k in n. Now suppose that x squared is congruent to -1. Can I say that P divides x or not?
No.
If P divides x, then x squared would be congruent to 0. Agree or not? If P divides x, then P would divide x squared. Okay? Now, the idea is that then P doesn't divide x. P does not divide x. Right? Hence, since P is prime, the GCD of x and P is 1. Hence, by Fermat's theorem, I have that x to the P minus 1 is congruent to 1. Okay? Yeah? So far, so good. Now, what is that? Now, P minus 1 over 2 is a P minus 1 is an even number, right? P minus 1 is 2 plus 4k. So P minus 1 over 2 is an integer. I just took the square out. I factored out a 2, P minus 1 over 2, since P minus 1 over 2 is an n. What am I saying? Wait, sorry. Okay, flipped it. Okay, I just put the x squared inside and the p minus 1 over 12. Now, what is x squared by assumption? Mod p, what is that equal to? Minus 1. So this would be minus 1 to the p minus 1 over 2, congruent to 1 mod p. Now, p minus 1 over 2 is an odd number, since p minus 1 over 2 is 1 plus 2k. So minus 1 to the p minus 1 over 2 is just minus 1 plus 2k is congruent to 1 mod p. Now, what is that? This is just minus 1 is congruent to 1 mod.
Happens if p is 2.
Exactly. So this means that 2 is congruent to 0 mod p. That's a contradiction. That means that p divides 2. But a prime number that is at least 3 cannot divide 2. Okay? Since p is bigger than
I mean, since 2 is not in the form of 3 plus 4k.
well, not 2 is not the form of 3. P, a prime number with the form 3 plus 4k can divide, doesn't divide 2, basically.
Yeah.
Okay. But if you take something 3, okay, so please not do this exercise. 15 of you ask this, and it's a cool idea. I mean, it's a cool. Now, a cool proof would be using Lagrange's theorem. Okay, I can tell you how. Maybe very quickly. Solve 2. If x squared is congruent to minus 1 mod p, then x has order 4 in UP. Okay? And then show that p minus 1 is not divisible by 4. Very good. Thank you.
Yeah, that's the most. Yeah. When you were trying to